is said to have a limit L as x approaches now. Approaching is also means tending. So as x approaches or tends to a number A, if the values this is the informal definition of limit of a function. So a function f of x is said to have a limit L as x approaches or tends to a number A if the values of the function f of x can be made as close as we like to the number L by taking x sufficiently close to this number A, and we need not to be exactly at the point A. What we mean is that we need to be getting closer and closer to the number x equals to A. So this is abbreviated by, or this denoted by, we write lim f of x, x approaches A equals to L. So this one is read as limit of f of x as x tends to or approaches A is equal to L. So this actually will be a very common expression throughout this chapter, that we write lim f of x, x approaches A equals to L, simply to mean that limit of the function f of x as x approaches A or x tends to A is equal to the number L. So that's what we call the informal definition of a limit. So let's give the formal definition of a limit. So formal definition of a limit. So in the formal definition of a limit, we use these Greek alphabets, epsilon and delta. So this is read as epsilon. This notation is called delta. So when you want to define a limit formally, we use this Greek alphabets, alpha and delta. And this is how it starts. So we say that a function f of x approaches the limit L as x approaches a, and this is written as lim f of x equals to L as x approaches a if for every positive if for every positive number epsilon. Remember, when I write epsilon greater than 0, I mean epsilon is positive. They exist another positive number delta, possibly depending on epsilon, such that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus a is less than delta. And because we have already said that delta is positive, then we say that this absolute value is between 0 and delta. So this is the formal definition of a limit. That a limit, a function f of x approaches a limit L as x approaches a or as x tends to a. And this is how we write this statement. If there exists a positive number, if for every positive number epsilon, there must exist another positive number called delta, which depends on epsilon, such that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus a is less than delta. So note, we usually use formal definition of a limit to prove that a given limit exists. Formal definition is not used for evaluation of limits. So get it right from the start that this definition we are giving is used or is only used to prove that a given limit exists, but is not used to evaluate limits or to solve limits. So we'll give examples to illustrate what this really means. Examples. Prove the following limits. So verify the following limits. So when a question asks you to verify or to prove a limit, then it requires you to use the formal definition of a limit to show that the given value of L for the given f of x is a correct number. So the first one, limit as x approaches 1 of 2x plus 3 is equals to 5. I want you to pay attention because when you are asked to solve such problems, assume in an exam setup or a CAT setup. So you have actually to follow the same trend in terms of argument to arrive at the conclusion that the given limit is true. So in such kind of problems, so the proof, so we say that here, what is our A value? If you are to compare the problem and the definition we have given, what the value of A?
1.
A is 1, correct. What is f of x?
2x plus 3.
2x plus 3, correct. And what is L?
5.
L is 5, correct. So that's the first step. You define your A, you identify the f of x, and then you identify the L value. And then you start by saying, or you assume that the positive number epsilon exists. So we say let epsilon greater than 0 be given. So that's the first assumption we make at the start, that let epsilon greater than 0 be given. So the goal is to find delta greater than 0 so that absolute value of f of x minus L is less than epsilon whenever x minus A is less than delta. This is the definition of this is the formal definition of the limit. So then now we start by what we have, the values we have for A, f of x, and L to fill in this definition. So absolute value of f of x minus L is the same as absolute value of, where there's f of x, I put 2x plus 3, where there's L, we put 5. Then what is 2x plus 3 minus 5?
2x minus 2.
2x minus 2. So this is the same as absolute value of 2x minus 2. Then 2x minus 2. What can you say about that expression? 2x minus 2.
Less than epsilon.
Yeah, so by definition, this should be less than epsilon. And then you say whenever absolute value of x minus A, which is 1, is less than delta. That is line 1. Then we can clearly see that 2x minus 2 can be written as, so i.e., This I can factor out to, so 2 into x minus 1 is less than epsilon whenever x minus 1 is less than delta. This is just the same definition. But then when you are discussing about real numbers, so you know that if I have two real numbers, a and b, absolute value of a times b is the same as absolute value of a times absolute value of b. These are results you know from discussion on real numbers. So when we have 2 times x minus 1 is the same, absolute value of 2 into x minus 1 is the same as absolute value of 2 times absolute value of x minus 1. So using this property, then we'll have absolute value of 2 times absolute value of x minus 1 is less than epsilon whenever x minus 1 is less than delta. And what is absolute value of 2? What is
2.
the absolute value of 2?
2.
Absolute value of 2 is 2, correct. So this is the same as 2x minus 1 is less than epsilon whenever x minus 1 is less than delta. Remember, what these things I'm writing is not fashion. Every time I'm writing whenever absolute value of x minus a is less than delta is part of the definition, and that's the process how we do the argument. So then now it is easy. We can remove these two by dividing through by 2. So we have absolute value of x minus 1 is less than epsilon over 2 whenever x minus 1 is less than delta. So what does this line tell us about the value of delta?
That the value is epsilon over 2.
Correct. So because you see all these are relating absolute value of x minus 1. So these numbers must be the same because we have exactly the same form of the inequality. So we choose, or we can say if we choose, delta equals to epsilon over 2, then we are done. So that is the proof of that first limit, that the ones you have assume that there's a positive number epsilon greater than 0, then the definition says that the absolute value of f of x minus L is less than that epsilon whenever absolute of x minus a is less than delta. And we can say that we have reduced the expression for absolute value of f of x minus L to a point whereby we are getting the same value at the absolute value of x minus a. And then we relate the value of epsilon expression and the value of the delta expression. So second problem, verify that the limit as x approaches 2 of 3x plus 1 equals to 7. So we'll do this, we'll work the problem in the same manner. Here, a will be 2, f of x is 3x minus f 3x plus 1, and then L is 7. So the proof for this is that we let epsilon greater than 0 be given, or simply let epsilon greater than 0 be given. So we show that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus a is less than delta, given that a is 2, f of x is 3x plus 1, and L in this question is 7. So that's the beginning of the proof. So once you have this, then your argument is from this absolute of f of x minus L less than epsilon. So you play with that expression up to the point where you will arrive at an expression which actually takes exactly the same form as x minus a absolute expression. So absolute value of f of x minus L would be the same as absolute value of 3x plus 1. L is 7, which is the same as absolute value of 3x. Now 1 minus 7 is? Minus
6.
6, less than epsilon.
Negative.
Whenever absolute of x minus a, and our a is 2, so whenever absolute of x minus 2 is less than delta. That is line 1. So this tells us that now 3x minus 6, what is common?
3.
3. So I can write this as absolute value of 3 into x minus 2 is less than epsilon whenever absolute of x minus 2 is less than delta. So just rewriting the previous line by factoring 3, which is common. Remember, the goal is actually to ensure that the part which has an epsilon, left-hand side reduces to the same form as the part which have delta. So this is the same as absolute value of 3, absolute value of x minus 2 less than epsilon whenever absolute value of x minus 2 is less than delta. Now, what is the absolute value of 3?
3.
3. So this would be 3 absolute of x minus 2 is less than epsilon whenever absolute of x minus 2 is less than delta. Then what do we do? What's the next step?
Divide by 3.
Yeah, divide through by 3. So we have absolute of x minus 2 is less than epsilon over 3 whenever absolute of x minus 2 is less than delta. So what does this tell us about the value of delta?
Epsilon divided by 3.
Yeah, so if we choose to be epsilon over 3, then we are done. So that's what we do for that given problem. So example C or 3, given that limit as x approaches 3 of 4x minus 7 is equals to 5, and epsilon equals to 0.01, find delta. So we have been given the limit of the function f of x, which is x minus 7, to be 5, and then x approaching 3, and the value of epsilon is given as 0.01. So we need to find delta that corresponds to 0.01. So in such cases, it's exactly the same process, what we have done previously, to get the relationship between the delta and epsilon. And once we have the relationship between delta and epsilon, we will will insert or substitute the value of epsilon as 0.01 and solve for delta. So solution for this. So we need first to get the relationship between epsilon and delta, which is the same thing as going through the process of proof of this limit existing. So let epsilon greater than 0 be given. So we need to find a delta which is also positive, such that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus a is less than delta for a equals to 3, f of x equals to 4x minus 7, and L equals to 5. So absolute value of f of x minus L will be given by absolute value of 4x minus 7 minus 5. And what will be the reduced form of that expression?
For x minus 12.
4x minus 12, correct. 4x minus 12 less than epsilon whenever absolute value of x minus 3 is less than delta. That's line 1. Then this means what is common for x and 12? 4. So factor out 4. So x minus 3 less than epsilon whenever absolute of x minus 3 is less than delta. Then this will be absolute value of 4 times absolute value of x minus 3 less than epsilon whenever x minus 3 is less than delta. What's the absolute value of 4? 4. So I have 4x minus 3 less than epsilon whenever x minus 3 is less than delta. So what's the next step?
Divide by 4.
Yeah, divide through by 4. So I have x minus 3 absolute less than epsilon over 4 whenever x minus 3 is less than delta. So what does this tell us about the value of delta?
The value is epsilon over 4.
Yeah, so this means that delta is the same as epsilon over 4. So this is like now the formula connecting the number delta and the number epsilon. So then now it becomes very easy to find the value of delta. So when epsilon is given as 0.01, this implies delta will be 0.01 divided by 4. So what will be the delta value?
0.0025.
0025, correct. So this is the value for that. Then second last example, verify that limit as x approaches 2 of x squared is equals to 4. Is exactly the same process that we have been doing. So we start by assuming that the positive number epsilon exists. So the proof, let epsilon greater than 0 be given. So once you have a positive epsilon, then the goal is to find another number delta, which is also positive, such that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus A is less than delta. And in our case, we have A is 2, f of x is x squared, and L is 4. So then now, absolute value of f of x minus L will be absolute of f of x is x squared, L is 4, less than epsilon whenever absolute of x minus 2 is less than delta. So then now, what should we do now in the next line? If you can follow through from the previous examples, what should we do?
Find the common value.
Yeah, so what is the factorization of x squared minus 4?
X minus 2x plus 2.
Correct. So this is the same as absolute value of x plus 2 times x minus 2 less than epsilon whenever x minus 2 absolute is less than delta. Then did the same thing as absolute of x plus 2 times absolute of x minus 2 less than epsilon whenever absolute of x minus 2 is less than delta. Please note from the start that these Greek numbers, delta and epsilon, are assumed to be very, very small numbers, but positive. Very, very small positive numbers. So epsilon and delta are supposed to be very, very small, but also positive. So whenever you are arguing out, always put that into consideration that all of them are positive and they should be very, very small. So naturally, if you are to follow the same trend from the previous examples, we expect the left-hand side of the part which relates the epsilon to take the same structure as x minus 2 absolute. So then I will have absolute of x minus 2 is less than epsilon over absolute of x plus 2 whenever x minus 2 absolute is less than delta. Just to ensure that the left-hand side of the part which has an epsilon is the same as the left-hand side of the part which has delta. But remember, x is a variable, it's not a number. So then now we have to get the numerical value of this expression of epsilon over absolute of x plus 2, but putting in mind that we need that number to be very, very small. This is how we argue out. So because we have said that we know that both delta and epsilon are very, very small numbers, so we'll say assume that this delta is a number less than or equals to 1. And there's nothing special with number 1. I'm only using 1 for convenience because we know that the number is positive and very small. So then now when I pick 1, then it's very easy to deal with 1. Another person can as well pick a half or a quarter or an eighth, but 1 is still okay. The smallest positive integer. So when we say we are assuming that delta to be equal or less than 1, then this implies that because we already know this relationship that absolute of x minus 2 is always less than delta, so the place where we have delta we can replace by 1. So we'll have x minus 2 less than 1. Because when I say delta is less than or equals to 1, then it means that where there's delta, I'm allowed to replace by 1. And you know from your discussion on real numbers, properties of real numbers, if I have the absolute value of a number a less than k, means a is between minus k and k, provided that k is a positive number. So if you write absolute value of a is less than k for k positive real number, then you simply mean that the number a is between minus k and positive k. Similarly, when you write absolute value of a less than or equals to k, means minus k less than or equals to a less than or equals to k. These are properties of real numbers that we did in basic mathematics. So when we have absolute of x minus 2 is less than 1, then using this property of real numbers, then this simply means x minus 2 is between minus 1 and 1. So what is the range of value of x? So if you solve, if you are to solve for x, so simply mean that for me to get an x here, I add both sides, all the part of this inequality, I add 2. So 2 plus minus 1 is this from 2 up.
1.
1. And then when I add 2 here, then I'll just get x. And then 1 plus 2?
3.
3. So then that means that the condition of x less than delta less than or equals to 1 means that the value of x will be between 1 and 3. Remember, our objective is to get the numerical value of the number x plus 2, which will make the fraction epsilon over x plus 2 very, very small. So x plus 2. So what is the, if I have a fraction, a over b, I have a fraction, say a over b, and I don't change the value of a, but I want this fraction to give me a very, very small number. What should be the size of the denominator? Should it be more or less for me to get a very small value of the fraction?
More.
Should be more.
More.
When you make denominator larger, then keeping the numerator constant, then you reduce or you make the value of the fraction very, very small. And that's our objective, to get a very, very small value. of this fraction here. So which means then, for us to get a very, very small value of epsilon over x plus 2, then we expect x plus 2 absolute to be a very, very large value. I remember we are saying that x is from 1 to 3. So what makes x plus 2 larger? Is it when you replace x for 1 or when you replace x for 3? To get x plus 2 to be a large number, do we replace x for 1 or x for 3?
3.
X for 3.
3.
When you fix 3, then 3 plus 2 will give you 5. So this denominator here will be, so from this point here, so we'll have absolute of x minus 2 will be less than epsilon over now 3 plus 2, which is 5, whenever absolute of x minus 2 is less than delta. So please note that in this, don't get confused here. This, yes, I know this. We are writing this one as a strict inequality. So they are strict inequality. So the key thing is that x is bounded from 1 to 3. So which means that if I pick 3 itself, in fact, I'm actually making the value of x to be large as I can. So that's why I'm just using this number 3 the way it is. And there's no penalty here. Even if you interpret this one as less than or equals to, less than or equals to, still will be allowed. There's no problem. So this tells us that absolute of x minus 2 less than epsilon over 5 whenever absolute of x minus 2 is less than delta. So what from this line itself, what would be the value of delta? As we have done in the previous examples, that tells us that delta should be taken as
Epsilon over 5.
epsilon over 5, correct. So don't forget that now, the first thing was to let epsilon, the delta to be less than or equals to 1. And then after arguing out, then we are saying that still also by that one, then this is another value that delta can also take. Remember, epsilon is a very small number. That's the much we know about the number epsilon. It's a very small positive number, but we don't know the exact value of that value epsilon. And because our objective is to ensure that both epsilon and delta should be very, very small numbers, then the choice for delta will be the minimum of the two numbers. The one that we have assumed is 1, and after arguing out, we are finding that delta also should be equated to epsilon over 5. So therefore, we choose delta to be the minimum of these two numbers, 1 and this number epsilon over 5. So the smaller of the two is what will be taken as epsilon, what will be taken as delta. So delta in this case, when now we have a quadratic function, is not one single value. It will actually be, in your argument, you'll get two numbers which you qualify to be equated to delta. But because we want the delta to be very, very small positive number, then the verdict will be just pick the minimum of the two given numbers. So many more other examples on the same arguments of proofs of limits are given in the link that I shared. So you should be able to follow through and see how we also argue for other problems. Similarly, at your own free time, you can also check this. Prove the following limits. So 1 is limit as x approaches 3 of x squared is 9. 2, limit as x approaches 4 of x squared plus 4 is 20. 3, limit as x approaches 2 of minus 2x plus 7 is 3. And then lastly 4, limit as x approaches 1 of x over 3 plus 2 over 3 is equal to 1. So at one free time, work out those limits. So I give a 5 minutes break, and when you come back, we discuss other things.
Shows.